Thank you, Shane. Welcome, everyone. We are excited to have you online for this webinar series. We have participants from all across the world, and we are really excited to have you on board. And thank you for joining us. So the objective of this webinar is to introduce you to our project funded by NASA, where we have citizen scientists deploy low-cost sensors to understand local air quality in conjunction with the satellite data. So we are eager to have your participation as citizen scientists to accomplish the goals of this project. This is a collaborative project between RTI, USRA, South Coast Air Quality Management District, and NASA. In today's webinar series, we will provide an overall introduction to the project, and I'll do that. Following that, we have our colleagues from the South Coast Air Quality Management District talk about the history of air quality in Southern California, as well as provide an introduction to the low-cost sensors, a specific type of low-cost sensor that we'll be using in this specific project. After that, we have colleagues from NASA and USRA talk about the satellite data and a live demonstration of the Worldview web interface. Finally, we'll be closing out the webinar with information on how all of you as citizen scientists can help this project, as well as help understand the air quality around you. And in the end, we'll open it up for a Q&A session. Okay, so to introduce the project, so I am Prakash Doraiswamy. I'm a principal air quality scientist at RTI International, which is a non-profit research institute focusing on improving human condition by turning knowledge into practice. I have my colleague here, Carmen Mills, who will be talking about the citizen science aspect at the very end of this webinar series. So why are we even worried about air quality? Ambient particles, we are going to focus mainly on the particles in this webinar. So ambient particles come in various size and composition. It consists of a mixture of solid and liquid droplets in air. PM 2.5, often referred to as fine particles, as you see in that image below there, are particles that are less than or equal to 2.5 microns in aerodynamic diameter. For context, the human hair is about 50 to 70 microns in diameter. Now, these fine particles have been linked with multiple health effects, including cardiovascular and respiratory effects such as asthma. So when we look at the impacts of air pollution on a global basis, this graph here is from a recent paper published in The Lancet by Landrigan et al., which shows that environmental pollution, that is the deaths related to environmental pollution, that's across air pollution, water, occupational and soil and chemicals, together account for 9 million deaths, of which air pollution alone contributes about 6.5 million deaths. So that's about 70% of the total mortality attributed to environmental pollution. Now, when we look at how this early mortality is distributed across, spatially, you can see that on the top left of the map here, on the top left, shows the absolute number of deaths, while on the bottom right, it shows the same number of deaths, but normalized by population, so per 100,000 people. So once we normalize it, it is obvious that much of these deaths occur in low and middle income countries. And in all of my slides, I've indicated where this information is from. So this particular map is from the State of Global Air, which offers a very nice interactive tool to visualize the air quality and health impacts. So that brings us to the project motivation. So in order to manage air quality, then air quality monitoring is a fundamental component of the overall air quality management framework. So to measure what's in the air, fine particles specifically that we are focusing here in today's webinar, so we have on the left the reference methods, which are point measurements, but are quite expensive and therefore are spatially sparse. But these are considered the gold standard because they have been evaluated and they've been shown to provide accurate, reproducible data. In the middle, we have satellite data, which offers global spatial coverage that is freely available. However, it is a column metric, so it is think of it as a camera looking from top above the atmosphere, and therefore it is looking through the whole atmospheric column. And on the very right here, we have the low-cost sensors, which have been increasing exponentially in the market in recent years. So these are also point measurements, but they are relatively cheap compared to the reference methods, and therefore there's a potential for broader spatial coverage. However, the downside is that they are less accurate compared to these reference methods. So what we are trying to do in this project is to bring together these different sources of data, the low-cost sensors and the satellite data, and see how we can develop an integrated data set that takes into account the advantages of the different data sources. Shortly, my colleagues from the South Coast Air Quality Management District will talk about the sensors, as I mentioned before, and following that, we have colleagues from NASA and USRA who will talk about the satellite data. So our overall project objective is to then examine how such a citizen scientist-based low-cost sensor can be used to generate particle data that is spatially and temporally resolved, and at the same time that is of high data quality. And as I said, our whole goal here is to complement the satellite observations in a sustainable manner. So this infographic here gives our overall project concept. This project takes place in two phases. Phase one is already complete. That happened last year. And that was basically a feasibility study to examine whether the deployment of such low-cost PM2.5 sensors in real field environments is feasible as part of an ambient air quality network. Now in phase two, which is the focus of this work, it's a 3-year period that we are going to be working on this project. Phase two, we will expand that preliminary deployment that was done in phase one to 3 regions, expanded in the Southern California region in Los Angeles Basin, in Raleigh, as well as Delhi, India. The idea behind that is we have 3 regions with different particle loadings and different particle composition. Los Angeles may have high particle concentrations in the US context, but on a global basis, it probably falls in the medium air quality range. Excuse me. Delhi obviously has been experiencing high levels of particle pollution, and Raleigh represents an area of very low particle concentrations. So what we're trying to do is to see how these sensors respond under these different conditions of particle composition, size, and characteristics, as well as how the relationship between the satellite data and the sensor data changes across these three regions. And so that's where all of you as citizen scientists will come in. So our goal is to collect continuous, reliable air quality data in a sustainable manner. If you register as citizen scientist for this project, we will work with you to collect PM 2.5 data using the low-cost PM 2.5 sensor, and also work with you in interacting with the satellite data. So stay tuned to learn more about the low-cost sensors and how the satellite data are helpful to understand the surface-based air quality. Further, we will also inform you about individual workshops that are being planned in each of these regions to have more interactive sessions on using these sensors, as well as applying the satellite data to examine scientific questions of your own interest. So to learn more about our project, please feel free to browse this website here. It's aqcitizenscience.rti.org. And there are various resources on the website, also a link for you to sign up as citizen scientists. And so that brings to the end of my presentation. I will now turn this to our colleagues at South Coast Air Quality Management District, who will now talk about the sensors and provide a historical perspective of the air quality in Southern California. Thank you.